Select the missing reagent required to accomplish the following transformation. So if we take a look at our starting material, we see we have a ketone, and we're treating this ketone with LDA. So that's lithium diisopropylamide, which we hopefully remember has this structure. So this is the diisopropylamide, the lithium counterion. So this is a really, really strong base. So what that's going to do is it's going to convert this ketone completely into the enolate. So we can have this amide is going, and this lithium is just a counterion. It's not bound to that, right? This is the diisopropylamide. So this is just like an ion pair, right? So this is going to remove that hydrogen and completely convert this into the enolate. So we can draw this enolate. Okay, and you've got the lithium counterion nearby. All right, so that's what the LDA is doing. So this is a strong base, a very strong base. And so we're using this for complete conversion to the enolate. So what that does is that prevents you from having some of this enolate and some of this ketone together in the solution where they might come together into a self-aldol reaction. Okay, so we want to see is try to find where we have these atoms in our product. So hopefully we can see these two carbon atoms right here are right here. So our new bond in the product is to here. So what that means is that if we're doing this reaction, and this is a directed aldol reaction, so you're taking one carbonyl component, converting it completely to the enolate, and then it's going to add to another carbonyl compound. So when it adds to the other carbonyl, it can add to something like this. So I'm just going to use some R groups on here. And so this can attack, and it's going to form a new bond to what was the carbonyl carbon. And this looks like it's undergoing a dehydration in the end. So what we want to recognize is that where this carbon 2 is attacking, that this used to be the carbonyl. So we can highlight that as a carbonyl. So we've highlighted it there in orange. And so we want to find out what that carbonyl looked like, what this R groups look like. So we can draw the carbonyl. Again, just kind of highlight that carbon. And then you want to say, well, what's attached to it? So on one side of the carbonyl, we see just a line. And we have to remember that at the end of the line, if there's nothing drawn there, then that means that it is a carbon. So not a hydrogen. Resist the urge to draw a hydrogen there. The end of a line is understood to be a carbon. So this is a methyl group. So that means on one side of that carbonyl, you had a methyl group. And on the other side of the carbonyl, you've got this benzene ring. And opposite, so at the 4 position away from that carbonyl, you have this OCH3 group. And so we can recognize that this is option D. So this is, as we said, an example of a directed aldol reaction. So it's called that because you are directing what happens. So you're taking one component and you're giving it no choice. It has to act as the nucleophile because you're going to use a strong base and completely convert it to the enolate. And then you're going to slowly add in your second component, which would immediately react with that enolate in your aldol reaction.